And finally, let's talk about equivalence law. Here exists in chemistry 4 mathematical equations for equivalence law, but now we need to say 2 of them. All components in different reactions, so I mean all reactants and all products, had the same numbers of equivalents. You know that in chemical reaction numbers of moles are different. That's why we need to write coefficients for substance in chemical reaction. But numbers of equivalents always the same for all components in reactions. For example, as you see, reaction between substance A and B, the reactants, and products C and D. And it means, according to the law of equivalence, it means that numbers of equivalence for all substances A, B, C, and D are equal. But how we can calculate in this case numbers of equivalence? Of course, previously talked about equivalent mass, not exactly about numbers of this mass. You know how to calculate numbers of moles. It's a ratio between mass, any portion of all substance, and molar mass. Absolutely the same situation here. Numbers of equivalence, it's a ratio between mass of this substance, of this component in the reaction, and equivalent mass. But in different reaction, we use not just solid substance, for example, metals, or solutions or substance in the liquid form, but sometimes we have reactions with gases. For example, reaction between, as we see, metal and oxygen combustion reaction, or reaction between metal and acids, which give us pure hydrogen. And if we want to make experiment and we want to measure quantity of this gas in our reaction in our experiment, it's more convenient to measure volume than pure mass. That's why we can calculate as well numbers of equivalence, not just using masses of components, but uses volumes as well. So here we can calculate numbers of equivalence as a ratio between volume of substance, I mean gas, for example, hydrogen, oxygen, or any oxide, or and equivalent volume. So you know what does mean molar mass? Mass of 1 mole of any gas, but here we use equivalent mass, equivalent volume of 1 equivalent. And you know, sometimes students makes mistake here, and they mixes numbers of equivalence and equivalent mass. For example, we eat apples, green apples and red one. And green apples, it's big apple, and red apple, small one. So obviously that mass of one apple, red and green one, absolutely different. Here we can say like equivalent mass, but numbers of this mass, numbers of this apple, absolutely the same. So if you eat 3 green apples, according to law of equivalence, you need to eat 3 red one. But once again, mass, equivalent mass, or just one red or green apple, absolutely different. And according to this calculation, as you see in the first position, how to calculate numbers of equivalence, we can rewrite this equivalent law. So we can write a second mathematical equation, and we can say that all substances in our reaction react in equivalent proportions. What do I mean? That ratio between masses of all components in our reaction, for example here between substance A and B, or you can use C and D, it's a ratio between equivalent masses for substance A and B as well. Of course, we can recombine this formula. We can write mass over equivalent mass of one substance equal to the mass over equivalent mass for a substance. Or as well, we can use volumes. For example, substance B is gas in our reaction, and of course, instead of mass of this substance, we can use volume and equivalent volume. So it depends on the situation, depends on task, on reaction which we use or which we have in our situation. As I said, we have three mathematical formula, three mathematical equations for law of equivalence. But third equation we use for solutions. And before we write this equation, of course, we need to explain what's the measure, quantitative measure of all solutions. And in this situation, we need to talk about concentrations. Widely, we'll discuss this theme in next lectures when we will talk about solutions, non-electrolytes, electrolytes, about dispersed systems. But now we need to give the main concentration which we use in future calculations, especially in chemical kinetics. We need to use molar concentration, in chemical thermodynamics as well. So let's talk about the main concentration. First concentration is a mass fraction. What does mean mass fraction? It's a mass of the salt substance, pure substance, for example, pure salt, pure hydroxide, which contained in mass of all solution. So to calculate mass fraction, and as you see unit here, mass percentage, we need to divide mass of the salt substance on the mass of all solution, multiplied of course on 100%. Sometimes we use mass fraction not for solutions but for pure complicated substance. For example, we have oxide, and they know that a mass fraction of sulfur in sulfur oxides equal 50. So in this situation we can calculate, we can tell that mass of all substance, or if we tell about solution, mass of all solution equals 100 grams. So sometimes we say that mass fraction is a mass of the salt substance, pure substance, in 100 grams of all solution or complicated substance. Next concentration is a molar concentration, or we call it like molarity. We express it like Cm or M. All concentration, if we don't say specific of this concentration, we express through letter C. But exactly for molar concentration, we write it like C with index M. What does it mean? Molar concentration, it's a number of moles of pure substance, the salt substance, in 1 liter of all solution. That's why unit here is mole per 1 liter. One note that concentration we use for solutions, and concentration is a parameter, not mathematical operation. Because sometimes students make such mistakes. They try to say me that molar concentration is it's in numbers of moles just in the volume of solution. Which volume do you mean here? course, for example, I want to prepare a solution, for example, with molarity 2, solution of sodium hydroxide, and this number 2 exactly tell me about volume of this solution, concrete volume, exact volume of this solution. It doesn't mean that we just take 2 moles of this substance, dissolved substance, and divide on solution. How we can do it practically? Of course, it's impossible. But these 2 moles of pure substance contained in 1 liter of all solutions. So you need to feel this difference between solution, between preparation of this solution. It's like physical process, and calculation of molarity, mathematical operations. So please don't mix it. And third concentration, we call it like molar concentration of equivalent, or sometimes we call it like normality, normal concentration, and express it like C with index n and n. Almost the same like molar concentration, but in molar concentration we need to take numbers of moles for the dissolved substance, pure substance, but in molar concentration of equivalent or normal concentration, we take numbers of equivalent masses and as well dissolve it in 1 liter of all solution. And one note that exactly liter of solution, not pure solvent, for example, not 1 liter of water, but 1 liter of all solution. So it's less than volume of pure solvent, less than 1 liter in this situation, in this case. Let's see some examples of calculations of equivalent mass for different classes of substances. For simple substance in different, for pure elements in different substances, and for complicated substance. For example, we need to calculate equivalent mass for sulfur, but in complicated substance. For example, H2S, SO3, and let's take 2 acids, H2SO3 and H2SO4. But our task to calculate equivalent mass for pure sulfur. As you already know, we can calculate equivalent mass for simple substance or pure element as atomic mass for sulfur in this situation over valency of this element. But sulfur has different valency, and to determine which valency exactly we use in these calculations, we need to know which substance reacts in our example. So, first example, first substance, H2S. As we know, hydrogen always had valency 1, so how to calculate valency of sulfur here? H2S is a neutral molecule, so valency of all molecules is 0. For a hydrogen, valence is 1, so 2 multiplied or 1 is 2. In this situation, they see that valency of sulfur is well 2. So in this first example, in this first substance, equivalent mass for sulfur, its atomic mass equal 32 over 2. So 16 grams per 1 mole equivalent. Almost the same situation for oxide and 2 acids. For oxide, SO3, here is we can calculate valency of sulfur. Here it will be 6 because valency of oxygen always is 2. So in second example, we divide 32 over 6, and it equal approximately 5.3 grams. We can write unit like just grams here or gram per 1 mole equivalent. Let's continue our calculation for sulfur. Now we have 2 acid, H2SO3. Here valency of sulfur equal 4, so we need to divide atomic mass 32 over 4. It equal 8 grams. And the last example, sulfur acid, we need to divide as well atomic mass 32 over 6. Course valency of sulfur here in this acid equals 6. So as well in the second example, we have equivalent mass equal approximately 5.3 grams. So now you can see that in equivalent mass for sulfur can be different, and it according to it depends on a Z complicated substance. Now let's see examples of complicated substance, and let's calculate equivalent mass for whole substance. Now let's take examples of substances for all or for classes of substances. Firstly, let's calculate equivalent mass for hydroxide. Let's take sodium hydroxide alkali, and for sodium hydroxide equivalent mass equal, instead of atomic mass, we remember we to take molar mass of sodium hydroxide and divide on numbers of hydroxyl ions. According to periodic table, molar mass for sodium hydroxide equal 40, and as you see in this alkali, numbers of hydroxyl groups equal 1. So in this situation, equivalent mass and molar mass absolutely the same. Let's take example of acid, and let's calculate equivalent mass for sulfur acid. In previous examples we calculated equivalent mass just for pure sulfur in this acid, but now let's calculate equivalent mass for all acid. The same situation, we take molar mass of all acid, but now we need to divide it on numbers of hydrogen cations. Molar mass, according to periodic table, in this situation equal 98. And as you see, in sulfur acid, we have just 2 hydrogen, 2 cations. And in this situation, equivalent mass equal 49 grams. Let's calculate equivalent mass for oxide. Let's take carbon dioxide. The same situation, molar mass of this oxide, but now we need to divide this molar mass on numbers of elements which form this oxide. In our situation, it's in numbers of carbon, and valency of carbon as well. So, molar mass for this oxide equal 44. We see here that we have just 1 carbon atom, so we divide by 1. And valency for carbon here equal 4, so equivalent mass for carbon equal 11 gram. And the last example, we need to calculate equivalent mass for salt. Let's take this salt, aluminium 2, SO4, triple. For salt, we calculate equivalent mass as molar mass of this salt, aluminium 2, SO4, 3, and almost the same situation like for oxides. We divide molar mass of salt on numbers of metal which form this salt. In our situation it's aluminium, and valency of this metal. So molar mass for this salt is 342, and we see that we have 2 atoms of aluminium in our salt, and the valency of aluminium here equal 3. So equivalent mass for the salt 57 gram 1 mole equivalent.